Now, telescope itself is a marvel when it comes to engineering. It's a masterpiece. It starts from the launch vehicle, obviously. Now, once it is launched, launch vehicle job is over. But the launch vehicle, launch technology should be there. It was already there, and mostly the telescope was designed according to it fitting the launch vehicle of ESA, that is Ariane 5. After that, image processing is a very important part of it because that is what you are there to do. The next is cooling system, because your image processing will not be working that appropriately if your cooling system is not that good, because like I said, infrared sensors should be cool. And the reason is the same. You're trying to look at very distant dim images. So the photons or the signature that you're getting from that distant object, the signal is very low. So sometimes you are going to get as low as 1 photon per second, which is extremely low. So the farther you want to look, the cooler your telescope should be, and thus cooling system is extremely important. And finally, the sun shield is very important because, like I said, there has to be a difference of temperature maintained, again coming back to the cooling one. The mirror itself, the kind of 3 cameras or reflectors about which we are going to now start to discuss one by one. So I'm going to put the images on the screen. People who are going through the audio version, it would not be that appropriate, and that is why Spacecast does require the video version. So we can start discussing with the sun shield. The sun shield, the main objective of that is to act as an insulator, maintain a temperature difference of close to 300 Kelvin, higher than that. The side facing the sun is going to be at 83 degrees centigrade, right? And then there are layers of insulation. And that is the thing when it comes to radiation insulation. Even if you look at nuclear power plants, and if you look at the shielding, that is the outermost part of any nuclear power plant, that is the dome that you see, that has layers of insulation. And even the thermoses earlier used to have layers of insulation. Why layers are good? Because in general position, if you are sitting on Earth, layers will be having air in between, and air is a tremendous insulator. You know what's worst as an insulator? Vacuum. And that is why new age thermoses have vacuum in between 2 layers. They have like all the air sucked out, and vacuum is going to act as the best insulator that you can have. No other material will be able to do so. Now, why is that? Well, because vacuum will have only one mode of heat transfer, that is radiation. Okay. Now, since there's no material over there, there's no gas, you cannot have conduction, you cannot have convection. Okay. But then again, Ashish, you said that we are having kind of a very fast rate of heat exchange when it comes to radiation. Then on Earth, if I'm having 2 plates and in between there's vacuum, won't I have a faster rate of heat exchange? And I think that this is what that lady wanted to say when she said that heat transfer because of radiation is quite slow. Now, please understand, the radiation heat transfer comes into effect only when the temperature difference between the 2 bodies are extremely high. Does radiation heat transfer takes place on Earth? Yes, it does. Right now, there's a radiation heat transfer taking place between me and the mic as well. But that is very negligible. Right now, is convection heat transfer taking place between me and the mic? Yes, it is, but very negligible. Right now, is conduction taking place? Not yet, but now it is, because now I'm touching the mic. So now I'm touching the mic. What kind of heat transfer is taking place between me and the mic? All 3: conduction, convection, and radiation. But the thing is that temperature difference between me and the mic is very, very low. Got it? And that is why you are not going to face any heat transfer. Maybe a topic that we can cover later. There's another question, that why do you think that this metal seems cooler even if it is at exact same temperature as, let us say, a phone made of plastic over here? That's a completely different topic. It's about what you feel, not exactly about what it is. But in real life, on the surface of Earth, there are few places where radiation heat exchange is dominant. And one example I can give are the furnaces, where the temperatures are seriously high, like thousands of degrees centigrade. Why is that? See, radiation heat exchange really comes into the picture when temperature differences are very high. When temperature differences are high, you'll see that those three formulas that I talked about, radiation really takes over. So if you look at the camera part, okay, so there's one gigantic mirror that I know that all of you guys have seen. It is made of 18 different hexagonal plates. It is coated with gold, and it is coated with 0.1 micrometer of gold. Gold is very malleable. It can be stressed very thin. It's not a new technology. And obviously you want the reflective part. You want to avoid the weight part. Just below the gold, however, is something very interesting. These plates are made of beryllium. Now, why is it made of beryllium? Because it is a very light metal and it has a very high what we call Young's modulus. Young's modulus of beryllium is 300 gigapascal. And if you look at what Young's modulus actually is, there comes a little bit of mechanical engineering. Hooke's law says that stress is directly proportional to strain in the elastic limit. And Young's modulus E is the slope of that straight line within the elastic limit. So according to Hooke's law, till the elastic limit, stress strain curve will be a straight line. And if you look at it graphically, that slope is Young's modulus, that is stress by strain. So if stress by strain is very high, that means that you need a large amount of stress to cause any amount of strain. In simpler terms, stress is amount of load that you apply. It is proportional to it. Stress is actually the internal resistive force per unit area generated within the body. But obviously, it is proportional to the external force or load that is applied. Obviously, it is also inversely proportional to area of cross section. But you get the point. So, a high amount of stress is required to be generated within a body to create a very tiny amount of strain. Strain basically is change of length. If you look at the formula, strain's formula is change in length divided by original length. So in proportionality with the original length, how much is the change in length, or basically you can understand the deformation. So if Young's modulus is very high, the material is difficult to be deformed. So you are going to have a stable geometry of these mirrors. So there are 18 of these. All are beryllium plates and all are coated with 0.1 micrometer of gold. Why gold specifically? Now, obviously, gold is a good reflector, but better reflectors are there. For example, what you have in silver, right? But gold is a great reflector in infrared region. So if you look at the graph, which I'm going to put right now on the screen, then you'll see that a huge amount of stability is present when it comes to gold, when it comes to infrared region. And that's what we are looking for, and that is why we have selected gold. All right, so beryllium being lighter than silica glass, what you use in other mirrors, are still not reflective, and so you are going to require a reflective coating. So this is the first reflector. This is where the light is going to fall the first, which is in the direction opposite to the sun, protected by the sun shield, should be at a temperature of 40 Kelvin. And this is the big bucket you can think, which is going to collect all the raindrop, or in other terms, is going to collect all the photons from the distant parts of the universe. These are going to be first collected by this gigantic mirror made of 18 hexagonal beryllium plates coated with gold, and is going to be redirected towards the secondary mirror, which is sitting at the focal point of this first concave kind of mirror. Now, because it is divided in a lot of parts, it is possible to adjust the focal length depending on what you're trying to look at. And one thing I forgot to mention, why it is hexagon. Obviously, other alternative options would be triangle. Now, if you look at trusses, bridges will be having triangular portions. Have you seen at any frame? For example, in mechanical engineering, we have this one thing in automobile engineering, especially when it comes to BARC competitions. We call it roll cage. So majority of the part of roll cage will be triangular. 3 rods in triangular fashion. They will be welded because triangles are the strongest. But that is a different deal. It is what we can say. Trusses are a different topic. A triangle definitely would be stronger, but also these are nastier because they are having pointed edges. So the largest angle that you can expect out of triangle, a genuine triangle, would be close to 90 degree. Obviously there are obtuse triangles as well, but then again its area of cross section becomes smaller and smaller, and you're looking at a flat piece of material. But hexagons, it is possible to go for a larger angle, and ultimately they settle down. Obviously nobody knows exactly, other than the NASA scientists, what were the actual conclusion or calculations, but I can do my best to explain it in terms of simple science and engineering. So this is the first layer in terms of you looking from the side of the camera. Okay, now let us do this one thing.